Today's review is going to be on the substitution rule. So, the substitution rule is essentially the one main key idea behind it is that if you have a function or an integral that is too difficult to solve or you're not sure how to solve it, you're taking it and you're putting it in a form of something that you know how to solve. So if we have an integral that's f of some function, it's going to be g of x, and then you multiply this by the derivative of dx. So let's just say that we have this integral. Looking at this right away, we don't know how to directly solve this. But using the substitution rule, what we do is that you look for a pattern within your integral. And what we're going to do is we're going to pick some variable, use pretty much the standard one that everyone uses, and we're going to let that equal the g of x. Now, you can technically let it equal whatever you want, but in this case, this is the one that's going to work for us. And the reason it's easy to recognize this is because what you do is that you want to get rid of this. And you know that because it'll make it simpler, so then you're only going to be left with some function f of whatever. So in this case, where we're letting u equal g of x, we're going to be left with f of u. So what we want to do is that when you take the derivative of u, you can see here that it's going to give us this, because the derivative of g of x is gx prime times the differential of x. Let's do the chain rule. So what we can do is, this is a little math sign here, is when you circle the equal sign, that just means that you're going to jump a step, and then when you go back down here and circle again, it means you're coming back down here. So everything that happened here in the middle is just a way to kind of keep track of your work, a little method that I use. So it just kind of shows that you did something here in the middle. So we're going to let that equal that, and then plugging this back in, simply going to give us a function of u times du, because remember that we're simply just plugging in du for this right here. Now, that's how substitution rule works, and it's very simple and straightforward. Now let's try an example. Alright, so once again, we're going to have a function that's going to look a little bit intimidating at first, because when you have an integral like this, you don't know how to directly solve it. So what we're going to do is, you can see right away that it's going to be complicated, and we want to make this whole thing simpler. So let's try this. We're going to let u equal t squared. And the reason you can recognize this is because if you take the derivative of the u, which is going to be the derivative of t squared, you're going to have 2t dt. And within our integral, you can see that we have a t dt. So, if we're going to substitute that out, we'll simply just have du over 2 equals t dt. We're going to go back to our integral, and we're going to plug that in. So now we're just going to have sine of u is going to be equal to u du over 2, which is going to give you 1/2, because you can bring the 2 out in front. The antiderivative of sine of u is going to be negative cos of u plus c, because we have an indefinite integral. And now remember that we want to plug what we had back in for u. Okay, and that's our answer. That's how you solve indefinite integral or a definite integral using substitution rule. So, since I mentioned using the indefinite integral, let's go over an example or how to solve an indefinite integral using substitution rule. So it's going to be the exact same thing that we did before. Oh, sorry, that's b up top. You're going to have a, and you're going to have some function that's g of x times g prime x dx. Except now you have boundaries. So now, when you do the evaluation, when you let u equal whatever it is you're going to let inside, you now need to change the limits. So what you're going to have to do, you have to change the limits according to the substitution. So call this 1. What this becomes is that it's going to become similar as before. What we're going to have now is g at b and g at a for our limits of a function f of u d of u. Alright, let's go over an example of this. So, if you have the integral of 1 to 0 of cos times pi x over 2 d of x, what we're going to do is we want to simplify this. So we're going to let u equal what was in the argument for cos. And so what happens there is when you evaluate u at the upper limit, you end up with pi over 2, and u at the lower limit, which is 0, will give you 0, because you're simply plugging in that 1 for the x that you had there and the 0 for the x. So now, you take the derivative of that, that's going to leave you with just pi over 2, because the derivative with respect to x of x is 1. And now we're going to go and we're going to plug this all back in. So now our upper limit, as we just solved for, was pi over 2. The lower limit is 0. We're going to have cos of u, and that's going to be times 2 over pi du. So what that's going to give us is 2 over pi, and the antiderivative of cos of u is sine of u, evaluating that at the upper and lower limits. What that's going to do is that, well, we know that we always evaluate at the upper limit first. So, taking our constant in front, we're going to have sine of pi over 2 minus sine of 0. We know that that equals 0, and that equals 1. Therefore, 2 over pi is the answer. This is the end of our Calculus 1 reviews. For more videos on how to solve further in-depth questions on calculus, please see our Calculus Part 2. And this should cover anything that starts from volume integrals, so it's revolutions of functions around surfaces, all the way up to Taylor series expansions and series expansions. Thank you for watching our videos, and please see our next section, Calculus 2.